In this episode, we step into computer vision, which is the part of AI that deals with images and video, and we focus on the essential ideas that help you understand what vision models can do and what they cannot. Beginners often imagine computer vision as a model that simply recognizes what it sees the way a person does, but in reality, the model learns patterns in pixels, and the meaning you want depends heavily on how the task is defined. In cloud security and cybersecurity settings, you might not immediately think of images, yet vision-like problems show up more than people expect, such as analyzing screenshots of alerts, recognizing patterns in scanned documents, or monitoring physical environments that protect critical infrastructure. Even when your core data is not visual, understanding vision essentials helps you reason about the kinds of model families and evaluation challenges that appear whenever data is spatial and high-dimensional. Our focus will be on augmentation, detection, segmentation, and tracking, because these ideas define how vision systems are trained and how they produce useful outputs. The goal is to build a clear beginner mental model so you can talk about computer vision in a grounded, responsible way. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to understand that a vision model does not receive objects. It receives arrays of pixel values, and the model must learn to connect patterns of pixels to labels or locations. This is why representation and training data matters so much, because the model is sensitive to textures, lighting, and background context in ways that humans often ignore. In a security context, this sensitivity can be a risk because the model might learn a shortcut, like associating a certain camera angle or watermark with an event category, rather than learning the underlying concept you care about. It can also be an advantage because models can detect subtle differences that humans overlook, such as small changes in a screen indicator or consistent patterns in document formatting. Beginners sometimes think the model extracts meaning directly from the scene, but the model is only as good as the patterns present in training data and the task definition you provide. This is why computer vision work emphasizes data diversity, label quality, and evaluation under different conditions. In cloud security, where environments change, a vision model that relies on a stable background may fail when the UI layout changes or when lighting conditions shift. Understanding pixels first thinking helps you predict these failures rather than being surprised by them. Augmentation is one of the most important practical tools in computer vision because it helps models generalize by exposing them to realistic variations during training. Augmentation means you deliberately transform training images in ways that preserve the label but change the appearance, such as small rotations, crops, flips, brightness adjustments, or noise. The intuition is that if the real world can produce different views of the same object, the model should learn that those variations do not change the class. For example, a screenshot might be taken at different resolutions, a document might be scanned at a slight angle, or a camera might see a scene under different lighting. Augmentation helps the model focus on features that are stable under those changes rather than memorizing one exact appearance. Beginners sometimes treat augmentation as a way to create more data magically, but it is better understood as a way to teach invariance, meaning the model learns what should not matter. In security contexts, augmentation can also protect against simple evasion, because a model trained only on clean images may fail under small distortions or compression artifacts common in real workflows. Thoughtful augmentation is therefore a generalization tool and a safety tool. Augmentation choices must be aligned with task meaning, because not every transformation preserves the label, and careless augmentation can teach the model the wrong lesson. If your task involves reading text and images, heavy rotation or cropping can remove the very information you need, changing the label in a meaningful way. If your task involves detecting orientation or direction, flipping an image might invert meaning, making the training signal inconsistent. In security-related screenshots, some elements like icons and warning colors can be sensitive to brightness changes, and too much augmentation can make those cues unreliable. Beginners often apply augmentation without thinking about what the label represents, which can create models that perform worse because the training examples become unrealistic. A professional approach chooses augmentations that reflect real variation in how data is captured, such as different screen scaling or slight camera shake, rather than arbitrary distortions. It also considers the risk that augmentation can amplify bias, such as if certain lighting conditions appear more often in some environments and augmentation hides that difference rather than teaching robustness. Augmentation is powerful because it changes what the model learns to ignore, so you must decide carefully what should be ignored. When augmentation matches reality, generalization improves, and when it does not, the model becomes confused. Detection is one of the core vision tasks, and it differs from classification because it asks not only what is in the image, but where it is. In object detection, the model outputs bounding boxes around objects of interest and assigns class labels to those boxes. This is useful when multiple objects appear in an image, such as multiple icons on a screen, multiple devices in a scene, or multiple regions in a document. In security contexts, detection can support tasks like locating warning indicators in a screenshot, identifying specific symbols in a scan badge, or detecting objects in a physical security camera feed. The key idea is that detection adds a localization requirement, which makes the problem harder because the model must learn spatial positioning and not just global appearance. Beginners sometimes assume detection is just classification plus a box, but the localization piece changes evaluation and training because the model must be accurate in both category and placement. Detection also introduces thresholding decisions, such as how confident the model must be before it reports a box and how to handle overlapping detections. These choices affect false positives and missed detections, which in security contexts can influence workload and risk. Understanding detection is essential because it shows how vision systems move from describing an image to acting within an image. Segmentation is another core task, and it goes beyond bounding boxes by assigning a label to each pixel, effectively outlining objects or regions precisely. There are different segmentation variants, but the beginner-friendly concept is that segmentation provides a fine-grained map of what belongs to what. In a document context, segmentation could separate text regions from background or distinguish a signature area from a form field. In a physical environment context, segmentation could separate a person from the background or identify restricted zones. In cybersecurity contexts, segmentation can help when precise boundaries matter, such as isolating a highlighted region in a screenshot or identifying a particular UI panel. The advantage of segmentation is precision, which can support downstream actions like redacting sensitive content or measuring area-based changes. The cost is that segmentation requires more detailed labels, because pixel-level truth is harder to create than simple image labels. Beginners often underestimate labeling effort and assume segmentation is always better, but segmentation is only worth it when the task truly needs pixel-level detail. If a bounding box is enough, detection may be simpler and more reliable. Choosing segmentation wisely is part of defining the right problem. Tracking is the vision task that connects detection or segmentation over time in video, allowing you to follow objects as they move across frames. Tracking is essential when you care about trajectories, persistence, and behavior over time, rather than isolated snapshots. In security settings, tracking can be used in physical security monitoring to follow a person through a scene, to detect loitering patterns, or to verify that an object remains in a restricted zone. Even in screen-based contexts, tracking can apply to sequences of screenshots or recorded sessions where you want to follow a cursor, a window, or a specific UI element. The key challenge is that tracking must handle occlusion, changes in appearance, and fast movement, and it must decide whether the object in the current frame is the same one seen before. Beginners sometimes assume tracking is perfect because humans can track objects easily, but models can be confused when objects overlap or when the scene changes quickly. Tracking quality also depends on frame rate and camera quality, which can vary widely. In cloud security workflows, the tracking idea is also a useful analogy for sequence consistency because it emphasizes that you need to maintain identity across time rather than treating each frame independently. Tracking connects vision to temporal reasoning. Evaluation for vision tasks differs from evaluation for simple classification because you are often evaluating both what and where, and sometimes how consistent across time. For detection, you care about whether the predicted boxes match the true boxes closely enough, and you also care about whether the correct objects were found without too many false positives. For segmentation, you care about overlap between predicted and true pixel masks and about how errors cluster around boundaries. For tracking, you care about identity consistency, such as whether the model keeps the same object ID across frames and whether it loses and reacquires objects correctly. Beginners sometimes report a single accuracy number, but in vision, a single number rarely captures the failure modes that matter operationally. In security settings, missing a critical object can be far worse than a slightly imperfect boundary, and false positives can create workload or false alarms. Evaluation must also consider environmental variation, like different lighting, different camera angles, or different UI themes, because a model can perform well on one condition and fail on another. This is where augmentation connects directly to evaluation, because augmentation is meant to prepare the model for variations you expect to see. Thoughtful evaluation aligns metrics with operational consequences and checks robustness under realistic conditions. Vision systems also have failure modes that are important to anticipate, especially in security contexts where adversaries may exploit weaknesses. A model can rely on background context and fail when the background changes, such as when a UI layout is updated or a camera is moved. It can be fooled by occlusion or low-quality images, producing missed detections or incorrect labels. It can also exhibit bias if training data overrepresents certain environments, lighting conditions, or device types, leading to uneven performance across locations. In cybersecurity-related document analysis, a model might learn to associate a certain template with legitimacy, which could be exploited by an attacker who mimics the template. In physical security, a model might be sensitive to clothing colors or to camera glare, causing inconsistent tracking. Beginners often assume that models fail randomly, but failures often follow predictable patterns tied to data coverage and task definition. Recognizing these patterns helps you design monitoring, such as tracking changes in input quality and alert volume. It also helps you set expectations with stakeholders so vision outputs are used as evidence rather than as unquestionable truth. Overclaiming is avoided when you treat vision models as pattern detectors with known limits. Computer vision also intersects with privacy more directly than many other AI applications because images and video can contain faces, locations, and sensitive environmental context. In security environments, the temptation to use vision can conflict with privacy policies and legal constraints, especially when people are in the scene or when screens show confidential information. A responsible approach includes data minimization, such as focusing on specific regions of interest, redacting sensitive areas, and limiting retention. It also includes access control, because raw images are often more sensitive than derived features, and sharing them widely increases risk. Beginners sometimes think privacy concerns are solved by blurring names, but images can contain many indirect identifiers, and video can reveal behavior patterns. This is why governance must be built into the pipeline, including documentation of purpose, restrictions on use, and clear auditing of access. If a vision model is used for security decisions, explainability also becomes sensitive because showing example images can expose confidential context. Responsible use means balancing security benefit against privacy impact and choosing the least invasive approach that still meets the goal. Vision systems can be powerful, but they demand careful governance. Bringing everything together, computer vision essentials revolve around understanding how models learn from pixels, how tasks are defined, and how training and evaluation must reflect real-world variation. Augmentation teaches invariance by exposing the model to realistic transformations, but augmentation must be aligned with task meaning so it does not corrupt labels. Detection locates objects with bounding boxes, segmentation labels pixels for precise boundaries, and tracking connects objects across time, each adding complexity and requiring different kinds of labels and evaluation. In cloud security and cybersecurity contexts, vision can support analysis of screenshots, documents, and physical environments, but success depends on careful task definition, robust evaluation, and realistic expectations about failure modes. Privacy and compliance are central because visual data is sensitive and can reveal more than intended, so governance must be part of design. When you can explain these ideas clearly, you are prepared to choose vision approaches responsibly, evaluate them honestly, and integrate them into security workflows without overclaiming what the model sees. That disciplined understanding is what makes computer vision a practical tool rather than a risky novelty.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.